In examples 5.2.5 and 5.2.6, we take a function that has a power of 3 for x, and we graph it and find the solution for when it's equal to 15. We also have an inequality to solve. So let's use Desmos to check our work. In the reading, you can see they use a graph to take a look at what the function looks like. And then from the graph, they take the solutions from that. So in Desmos, what we're going to do is first put in the left side of this equation so we can see a graph of the function on the left. So it's going to be y equals negative 2x to the power of 3 plus x squared plus 16x. Now we can see part of the graph. We can notice that we probably need to zoom out. However, it looks like our domain from negative to 5 to positive 5 might be okay. So we're just going to zoom out a little. Actually, no, let's go ahead and change the graph settings and just change the y values so that they're a little bit wider, so to speak. So I'm going to just try negative 20 and positive 20. That was a guess, right? We have to learn how to do some intelligent guessing here. And it looks like that mostly does the job. I can click and drag to see this. And that's a pretty good picture of what's going on for that function. I'm going to scoot that over here to the left, and I'm going to get rid of this empty space by once again changing the domain, the x values, to go only out to about 5. Okay, so that gives me a nice picture of what's going on. And of course, we've seen before that to find when two equations are equal graphically, we take the first equation, which we've already graphed, and we take the second equation, y equals 15, it's a constant. And then where the two graphs intersect is where the solutions of this equation lie. So we can see at negative 3, 15, at 1, 15, and at 2.5, 15, those are the 3 points that represent the solutions to this equation here. And you can see here that they've checked one of these, right? We can go back and, if we need to, we can change this from y to f of x instead. And the reason I would do that is because it would allow me to do things like this. I could say take f and evaluate it at negative 3. And I can verify that that is equal to 15, and so therefore negative 3 is a solution. If I wanted, I could then look at what the value of 2.5 is. Again, it's 15. Okay, so that gives me the solution to example 5.2.5. Now let's look at 5.2.6, where we're asked to graph and solve the inequality. So we want values where this function is greater than or equal to 15. We already know where they're equal to 15. We got those 3 points. To solve this inequality, we want y values that are larger than 15. So anything on this red graph that goes up and down, wherever we have values that are greater than 15, that's going to satisfy this inequality. Notice in the reading, they highlight those values on the graph by creating them in red. So everything above this dotted line is larger than 15, and that corresponds to this part of the graph in Desmos. Other places where the y value is larger than larger than 15, is this kind of like little mini mountain, right? And so we already know that those 3 points, let's go ahead and display them that way. We know that y is greater than 15 here, everywhere to the left of negative 3, and between 1 and 2.5. So if we look at the solution here, the solution is going to be written in interval notation here in the solution. So we're going from negative infinity up to negative 3. Notice there's a square bracket on -3, which means -3 is included, and that's because when x is -3, this function, the left side, is equal to 15, and our inequality is a greater than or equal. Same goes for the 1 and the 2.5. Those are closed brackets because both 1 and 2.5, at that point, at those points, the y values are 15, and then between them, it's above 15. So the solution to this inequality is the union of two intervals, the one from -infinity to -3, union with the interval from 1 to 2.5.